Unfortunately, not all of the formula of hydrate problems are given to us as simply as the first two that we had covered in the previous lesson. So sometimes the author of the problem will give you just all of the percentages that they found in the sample, and they could obtain that in a lot of different ways. And then from there, you have to determine not only how much water there is, but what was the original formula of the ionic compound in the first place. Sometimes you can predict what that will be just by looking at the combinations of elements, and some pretty common polyatomics that are out there, and you also know some of the charges of these cations, and so you can make some predictions, but it's always really good to follow through on the math. So we're actually going to solve this problem the exact same way that we've been solving other empirical formula problems in the past, which is essentially what we're doing here. We're looking at the simplest ratios, and so we're going to set this up the same way that we have done other problems. All right, so that is, I'm going to list out all of the different things here. So I'm going to be working with zinc, and there's 23% of this sample is zinc, and again, in previous videos we learned that we can assume that the sample has 100 grams, and so instead of writing down 23%, I'm going to write down 23 grams. And right away, I'm going to just follow up on that method of dividing by the molar mass of zinc, which is 65.38, to get the moles of zinc in the sample. So I'm going to go ahead and plug that in to my calculator right now. And that gives me 0.3517. I'm going to round that to a 9, so it was 17895. It kept on going, so I'm going to say 0.35179. Again, that's moles, right? That's moles of zinc. Important to know so I don't make a mistake or forget to divide, or I round too soon, and all those fun things that you might have encountered with empirical formulas. All right, so moving on, it's 11% sulfur. So sulfur, we're going to assume that there's 11 grams of it. The mass of sulfur should be 32.07. And again, dividing that out gets me a number of 0.342999. So I'm actually going to round that to 0.343 moles of sulfur. Either round it, or I'm going to have to write it out, and it's going to be super long. The next one is oxygen, and I have 22% oxygen. So oxygen, 22 grams, divided by 16, which is its molar mass. And I get 1.375. I'm actually not surprised by that, since right now I'm thinking we're probably working with sulfate, so there should be 4 oxygen atoms in this compound. So I'm excited because right now the zinc and sulfur are in a 1-to-1 ratio, which is what I was expecting, and then the oxygen looks like it's about 4 times as large. Now for water, this is a little bit different. We haven't done this before. It says 44% of this compound is water. So we're just going to write down water, but we're going to do the exact same thing. We'll assume 100 grams. So we have 44 grams of water. Now, instead of dividing by individual hydrogen, individual oxygen, we'll just divide by the molar mass of water. So 18.02. And again, I'm expecting this number to be bigger than some of the others, because it's what's going to be attached to my compound. So it's 2.4417 moles of water. Right now, the way that we have this set up, we're back in the exact same place we've been with every empirical formula calculation we've had in the past. We're going to just go through and divide by the fewest number of moles that were calculated. So in this case, we're going to divide by 0.343. And this is going to be close enough. The zinc is going to be close enough to 1 that we'll round that to 1. Again, we'll just divide by 0.343. And that's going to get us to a 1, obviously. Divided by 0.343. And I'm going to plug this in just to make sure I don't have any rounding issues later. That gets me to 4.0087, so perfect. So it's a 4. And then 2.4417 divided by 0.343. And I get a number of 7.1186. So I'm just going to say 7 on that. Again, this is all lab data, so there is going to be some freedoms in rounding out that water molecule that you may not experience when you are doing empirical formulas for regular, just like determining regular formulas with like ionic compounds or molar compounds. Sorry for my struggle there. I had a mental block. All right, so now I'm going to just write this out like I normally would. So I have 1 zinc, 1 sulfur, and 4 oxygens. So ZnSO4, which is kind of what I was predicting I would have. And then I have 7 waters. And I'm going to quickly name that. It's zinc sulfate, heptahydrate. So don't be intimidated by problems that give you a lot of percentages like this one did. Really just kind of go back to your empirical formula knowledge, set everything up individually in the order that it appears in the problem. Really just divide by the molar masses of everything that you're given, and then look at your moles and divide by the lowest number there. That should give you the exact numbers for the formula, and you should be good to go. So again, don't be intimidated by that. Another example of a problem that they could give you is where they're giving you the formula name, but they're not telling you exactly like how many grams of the whole compound are there, and they're not telling you like how much is lost, like how much water is lost after it's been heated. So again, we just approach these problems slightly differently, but we're going to rely back on our use of or understanding of empirical formula. So again, ammonium phosphate, I would highly, highly encourage you guys to write out that formula first. So we know that it's NH4, and that has a positive charge, and then we have phosphate, PO4, which has a 3 negative charge. So this one is actually going to be NH4, 3, PO4. Once you know that, go ahead and calculate out the molar mass. Again, this is part of what takes so much time. Is first you have to write the formula, then you have to calculate the molar mass of that. So when I calculate that, I get 149.10 grams per mole. That's going to be helpful information because you need it for the empirical formula part of this. So now I'm going to just assume that I have 100 grams of the sample, and I'm going to quickly walk you through this. So 73.42 grams of ammonium phosphate divided by 149.10, right? If we divide by the molar mass, we will get how many moles. So 73.42 divided by 149.10 gives me 0.49242. And again, that's moles of the compound. The next part here is just dividing out the mass of water, which should be 26.58 grams divided by 18.02. And that should give me my moles of water. And I get 1.4750. So we can already make a prediction about what this will look like at the end. I'm going to go through and divide then the moles of water by the moles of the compound, and that should work out pretty nicely. And I get 2.9954. Let me just show that step since this is a tutorial video. There's 2 ways I can do that. I can go through and divide both here by the lowest number of moles, which is what we've done a lot, or I can just go back to my empirical formula of hydrated compounds, and I know that my water just needs to be divided. This is going to give me obviously a 1, and then this is going to give me a 3. And so my empirical formula for this is NH4, 3, PO4 with 3 water molecules attached. And then the actual name of that would be ammonium phosphate trihydrate. It's interesting because students will actually get really, really good at doing what we consider to be the basic formulas, where you're taking and subtracting, how much water was lost, and then going through the steps. And then you'll get to a problem like this and be stumped because you're like, well, where's the data? Where are the numbers? But again, you can just go back to some of your roots of empirical formulas and assume that you have 100 grams of the compound, figure out those molar masses, figure out those moles and then do your division, and you should be just fine. All right. And then comes problems like 9 and 10, which is the one that we'll follow up on. And these ones typically would throw people for a loop because you're like, this is not like anything that we've done so far, and this doesn't make sense. And actually, a problem like number 9 is going to rely on your understanding of percent composition more than it's going to rely on any other skill that you have right now. So in a problem like this, they give you a sample, and this is borax, which is a common cleaning agent. You might actually have this in your house. Borax is one of those compounds that when you were younger and you were making slime in science, and it was a fun day where you got to like make slime out of glue and borax or some other substance, and usually borax is what is used to link the glue molecules, the polymers together. So you might have this laying around at home, and if you have a ton of glue and borax, go ahead and have some fun, right? Make some slime while you're sitting at home with nothing to do. All right, so in this problem, we're given 5 grams of borax, which is the Na2B4O7 with 10 waters attached. It was heated to remove the water. And the question is, what is the mass of anhydrous sodium tetraborate, which is the name of that Na2B4O7? What is the mass of that remains? And so again, a lot of times students will get there and like, where's the information? What am I supposed to do here? But if we look at this, we could actually calculate out We could calculate out the molar mass of the sodium tetraborate and the molar mass of the 10 waters, and we could add that together. If we know the total mass of 1 mole of that sample, we could figure out what is the percent composition of the sodium tetraborate. If we know the percent composition, we can multiply that times the 5 grams. All right, I know that might not be translating well to those of you who are more visual learners, so let me go ahead and walk you through that process. So if I go ahead and calculate out what is the molar mass of Na2B4O7, I'm going to write this out, Na2B4O7. The molar mass of that should be equal to 201.22 grams. All right, now we have 10 waters, not just one, so we're going to take 10 times the molar mass of water, and that's going to give me a total mass of 180.20 grams. Again, that's per mole of substance. So if I had 1 mole of the substance, I'm just going to add those two things together quickly, and then the whole thing is going to have a mass of 381.42 grams. All right, if I'm going to do the percent composition of anything, I'm going to take what I'm looking for over the total of the thing I'm studying, right? So in this case, the question is very specifically asking what is the mass of anhydrous sodium tetraborate that would actually remain. So I just want to work with the percent of sodium tetraborate in this whole complex. So I'm going to go ahead and take that and divide it by 381.42. And when I do that, that's going to give me the decimal, right? That's going to tell me what my percent is. I don't actually need to know what the percent is. What I need to know is how much of the 5 grams is corresponding to that. So I am just going to then multiply this whole thing times the mass of my sample. So 201.22 divided by 381.42 is 0.52755. So that tells me that roughly 52.76% of this compound is actually that sodium tetraborate. When I multiply that times 5, again, I'm not going to round at the very end here, I get a mass of 2.63777. I want to round to 3 sig figs because 5.00 grams had 3. So 2.64 grams of the anhydrous compound, and I'll just write out that Na2B4O7. Now, if we wanted to know what mass of water remained, I could actually do that one of 2 ways, right? I could go ahead and just take and subtract 2.64 from the 5 and get 2.36. The other thing I could do is I could take the mass of water, so 180.20, divided by 381.42, which would be the percentage of water in that compound, multiply it by 5. So either way, even though this question is only asking for the mass of one thing, I could determine the mass of both as soon as I know one. All right, this last problem is going to be very similar to what we were just doing. It's asking now for both. How many grams of water and anhydrous salt would you get if you heated a sample that was 9.42 grams? Again, we have to go through and figure out, what is the mass of FeNO3 Right here would be a great time for you guys to pause the video. Again, try this problem out by yourself and then come back to the end of the video and see if you were accurate. And hopefully I will be too. So the molar mass of this is 241.88 grams. 88 grams. And then water, we have 9 moles of water here. So 9 times H2O, 18.02, should give me 162.18 grams. When I add that together, the molar mass of this entire complex should equal 404.06 grams. And again, I want to just set this up. So I'm going to first look at the contribution of the iron 3 nitrate, like how much is in the sample corresponding to just the anhydrous portion. I'm going to divide that by the total sample mass. And again, just to take a slight little shortcut here, I have to go back up. 9.42 is my sample mass. So instead of writing everything out. So 241.88 divided by 404.06 times 9.42 gives me a mass of 5.639. So I'll say 5.64 of the FeNO3. And again, the simplest thing I could do to figure out water is going to be taking that 9.42 minus the 5.64, and that should tell me how many grams of water I have. So 3.78 grams of water. Now, one thing, I will be honest with you, one thing that my college professors would have us do on a formal assessment, you won't have to do this, but they would have us take those numbers and then show how you actually could get the formula based on those numbers. So we'd have to go back through and take like the 5.64, divide it by the molar mass of that, take the 3.78, divide by the molar mass of water, and just kind of walk through the problem the way that we would have done in the past, just to prove that our answers actually worked and will still get us back to that iron 3 nitrate nonahydrate compound. That's about it as far as the ways in which these problems will be approached in CITS Chem. Again, the most basic of them, they'll give you the starting mass of a sample, you'll heat the sample, you'll lose some water, and you go from there. Some of the more time-consuming problems is when they give you the percentages of every individual element and water in the compound, and you have to follow through on formula. Problems 9 and 10, I don't believe are very hard. It's just you have to shift your mindset. So you've been doing empirical formula, empirical formula, empirical formula, and now you have to shift your mindset and look at the compound as being a, what's the percent of something in 1 mole of that compound. So it's just a mind shift. But again, once you've done enough of those problems, it's like anything, your brain will recognize it. Your brain will acknowledge, hey, this is a percent composition problem more than it is anything else. All right, good luck with these problems at this point. Go ahead and do the more advanced version of that worksheet. Again, if you're struggling, if you're like, I can do the naming and writing compounds and I can do the basics, then stick with that. That there's no shame in that. If you are ready for a challenge, then work on these more advanced problems. If your brain is looking to be a little bit more stimulated right now, which some of us need, go ahead and jump in on these problems, do the more advanced. I'd always encourage you guys to push yourself to what you are feeling capable of and ready for, but not beyond that during this time. All right, good luck. And again, send questions if things didn't make sense or if you notice that I made a mistake. That could have happened very, very easily. There's lots going on in my mind too.